Okay, our next presenter is Sierra Monreal with NCI Southwest at NSU.
Thank you for the introduction. Hi everyone, my name is Sierra Monreal, and today I'm going to be discussing the details of my project titled Boron, Nitride, and Diamond Electronics. My advisor is Dr. Trevor Thornton, and my mentors are Eugene and Melly. Companies and industry are starting to pay more attention to boron, nitride, and diamond because they have been noted to have exceptional characteristics such as thermal conductivity and an ultra-wide band gap of approximately 5.5 electron volts, which makes these materials suitable for dissipating heat within high-power applications that require the material to withstand higher voltages. We are researching capacitors, which are circuit components that can store charge in between two metal plates. A metal boron nitride diamond capacitor can be used in extreme conditions, such as satellites, spacecraft, rovers, etc. We are fabricating diamond-based capacitors for high-power radio frequency applications, and a probe station and a semiconductor/component test system were used to characterize the sample's electrical properties. So this graphic shows the different layers of the metal boron nitride diamond capacitors. Our first layer is the contact metal composed of titanium, platinum, and gold, and we actually fabricated this in the clean room to make this contact metal. And then our next layer is the boron nitride layer, which has varying thicknesses within the experiment, and but however I specifically tested on 50 nanometer thickness. And then we have the boron doped diamond substrate, and it's important that this is boron doped because doping is a process in which we add a certain chemical element to a semiconductor in order to change its electric conductivity. So boron allows our diamond to be more conductive. And we will be measuring capacitance, which is the amount of charge that can be stored within the that can be stored when it is connected to a certain battery. And then shown in my diagram, the charge in the capacitor is flowing away from the positive plate to the negative plate. So as far as fabrication of the contact metal, we did this patterning process so that we could characterize the sample's electric characteristics. So as far as photolithography and development, this was just actually us just printing the pattern onto our substrate, and then metal deposition and liftoff were required so that we could put the titanium, gold, and platinum onto our pattern that we just made. And then this was the procedure that we followed to measure our sample. First, we identified the microscope images of our patterns and labeled the pads for easy identification during testing. And pads are the gold-looking circles shown in Figure 6. As you can see, there are various shapes and sizes, but we choose to take measurement of the circle-shaped ones because their area is easy to take, and that is important during graphing and analysis. Then we loaded our substrate into the probe station, and the live microscope feed was displayed on a media player, which allowed us to select each pad that we wanted to test. And the software that we used on the computer allowed us to apply the desired voltage and current placed on the pads. And we increased the voltage by small increments until we observed its breaking point. And we repeated this process a few times on various sized circle pads. To our understanding, we have so far established that as boron nitride thickness goes up, breakdown field goes down. However, during experimental research, we have noticed that the breakdown field was much lower within testing the 50 nanometer thickness than what we would have experienced so far. The reason this pattern is going downwards is because there are small scratches in our sample which can contribute to the defects during measurement. And these scratches are shown in figure 8. They're very faint, but you can kind of tell that they're there. So we're assuming that there's an outlier at the 50 nanometer point for this reason. The linear IV curve demonstrates the relationship between voltage applied and the current that flows through the device. It is significant to take note of this because we can determine conductivity, resistance, and breakdown point. An effective measurement properly showing where breakdown occurs is indicated by the current until there's a distinct upturn, which is in this graph shown just before 3 volts, highlighted by that red circle. We would also like to understand the benefit of analyzing the log graph as well, because we can observe the smaller details that don't seem as apparent in the linear graphs. Sometimes it's difficult to specify where breakdown occurs exactly, but since this graph is shown in smaller increments, it's more obvious to us. We can also observe the relationship between voltage and current is not right exactly at 0 right before the breakdown occurs. It slightly increases before we see that large break. The capacitance voltage curve shows the relationship between voltage and amount of capacitance, and it is, you can calculate it by using charge over voltage. And this result that we see right here in figure 12 is not desired because it shows that this device is not exactly a good capacitor. It slows the charge rather than storing it. Therefore, it acts more as a resistor. Ideally, a desirable result would be a graph that can withstand high voltage over a long amount of time, which would be demonstrated by a horizontal line on the graph. So we are expecting an inverse relationship between boron nitride thickness and electric field, and this can be calculated by voltage over distance. During actual testing, we experienced that the electric field was 0.8 megavolts over centimeter, but we expected that it would be 3 megavolts per centimeter, and this, once again, can be explained by the leakage that we discussed previously. In conclusion, my research determined that 50 nanometers of boron nitride was not an effective device because it showed evidence of leakage, and it wasn't exactly consistent with our previous research that we tested. And so in the future, we want to test more samples with a variety of boron nitride thicknesses and plot them on our curve so we can have more confidence in predicting the breakdown point when the metal boron nitride capacitors are used in real high-power radio frequency applications. Thank you. Any questions?